Good morning, good afternoon, good evening. It's an honour and a privilege to have this opportunity to be with you all here at this virtual DVCon 2021. Thank you for taking the time out of your busy schedules to listen to this presentation. Now, many of you may not realise that Cadence has been a public company for more than 30 years. And if we look back to the original IPO filing for Cadence in 1987, you can clearly see the founding principle of our company as one of design automation. Cadence develops, markets and supports CAD software products that automate, enhance and accelerate the design and verification of integrated circuits. By combining previously fragmented point tools into a unified flow under a new electronic design automation company, Cadence would enhance and accelerate this automation. Now fast forward to today, and nobody even talks about automation anymore. Automation is just expected. It's a fact of life. Nothing would happen without automation. What our customers look to us for now is a partner to help differentiate their products. It's not just about automation, it's automation with best results. And the challenges are not only at the design level, it's performance of the overall system that the chip goes in and performance of the end applications built on these systems. Our future is a world of intelligent connected devices with learning, sensing algorithms and customized user experiences. At Cadence, we feel perfectly positioned to rise to this new challenge of best performance. We call it our intelligent system design strategy. And there is no better place to highlight how this strategy is influencing our products and roadmap than in digital verification. Verification is a truly infinite problem. A chip with 1 billion gates has 2 to the power 1 billion possible states to verify. If you double the gate count on a chip, you square the number of behaviors that need to be verified. On a modern CPU or GPU, the number of verification cycles pre-tape out is approaching the age of the universe in seconds. That's a staggering amount of compute. At some point, our customers just make a judgment call that delaying their tape out further to hunt for more bugs would be more risky for business than the risk of taping out today. Essentially, their verification task is never done. They just hit a point on an asymptotic curve of coverage versus time where they say enough is enough. So how do we think different to partner with our customers on such an intractable problem like this? What does best verification performance even mean? Well, a good analogy we can look to here is the package delivery industry, FedEx, UPS, DHL, or even Amazon. Here you have millions of letters and packages that need delivering every day. And at first glance, the problem can also seem somewhat intractable. How is it solved? Well, first, you tackle the problem by deploying multiple engines with different trade-offs on key performance metrics: speed, reach, prep time. But you don't stop here. In the end, do we pick FedEx over UPS based only on which company has the best vans, trucks and planes? No. Winning performance comes down to the logistics of connecting all these engines together. Not wasting time moving from the plane to truck to delivery van. Not leaving planes sitting idle at the airport. Picking the best delivery routes. Picking the right number of trucks and planes. Picking the right airport and warehouse locations. This reminds me of a famous military quote many of you may have heard before. Amateurs talk about strategy. Professionals talk about logistics. And I think the same mindset is absolutely applicable to verification performance. It's not just about our verification engines. It's about how these engines are connected together to deliver the highest verification performance through intelligent verification logistics. Think about the logistics of which tests are best run on which engines, or which coverage challenges are best met with which engines. How many of each engine you need, when in the project to use which engines. All with the ultimate goal being to find and fix as many bugs as possible for the budget and schedule you've been given. Think of maximizing bugs found and fixed per dollar invested per day of schedule. We call this verification throughput. And this is our view on what happens when you apply an intelligent system design strategy to the problem of digital verification. Now, I guess I should conclude that no analogy is perfect, and I couldn't quite fit package delivery and formal into this paradigm. But hopefully you can all get the concept and see that in the context of verification, the principle obviously extends to include formal in this verification computational logistics mentality. So let's take a look now at just how important logistics is to verification throughput. This slide shows an example of daily simulation workloads for some typical modern design APs across Cadence's customer base. Running these workloads requires a lot more work than just the core simulation step itself. You have to prepare the regression run scripts, request and queue for resources on the compute farm, get access to hosts, initialize these hosts, load simulation data, and then finally actually run the simulation jobs. Then, after running the simulation jobs, you need to save data, generate reports, debug and triage the failures, and go make the necessary fixes to your design or test environments. And here's an example from one of these customers showing the total CPU time for running their simulation workloads as experienced by the end user. See the blue line in this chart. And then we've broken out how many of these total CPU hours are actually time spent with jobs waiting in the queue for compute access on that customer's server farm. Now, while many of you may be looking at this chart in disbelief, I assure you it's honestly something we see very often. The sheer scale of that 2 to the n verification problem, that the volume of jobs that are constantly being pushed onto the compute farms, they are always stressing. Verification is always overutilizing available compute farms. And so these challenges, they're very, very real. And I think, really highlight how critical the logistics of verification is to overall verification productivity. And here's something else you might find quite interesting. This slide shows a chart of the runtime for running a particular suite of simulation jobs across a range of different bare metal server types, i.e. different types of x86 or ARM-based blade in your data center. Now we've normalized the runtimes relative to the street price of buying that particular server blade, as in take the all-in price, for the CPU, motherboard, memory, disk, everything. So take the runtime and divide it by that cost to get, if you like, a throughput per dollar. And you can clearly see, a massive spread. And what's very interesting when we look at this data closely, the distribution. I mean, not only is the spread, we're talking, an order of magnitude here, not just 10 or 20%, but that spread has a very different profile depending on the tests that are being run. So again, pointing to, huge both opportunities and challenges around verification throughput in terms of the logistics of managing such a campaign. So hopefully now you can appreciate that just as it is for FedEx and UPS, the logistics of verification is a very important computational problem. And this problem compounds further when you consider the full suite of engines across a verification flow. So not just simulation, but also formal, running on that same x86 and ARM server farm, to accelerated simulation on an emulation system or a prototyping system, which would then be different types of bare metal compute. And in these cases, for your emulation farm and your prototyping farm, you have to consider the problem of what we call job shaping and job fragmentation, i.e., finding space and making sure you don't fragment available space in a dynamic queue-based environment, depending on different size and runtime of jobs. So this is, think of this more like kind of playing a game of Tetris or packing boxes in a delivery truck. So a lot of challenges, a lot of opportunities to optimize verification throughput beyond the underlying performance and scalability of the individual engines themselves. So at Cadence, we're really doubling down here. The way I look at this actually is that verification computational logistics is potentially the one engine to rule them all. And so we have a platform, a product called vManager. It's something we've really been investing in. It's seeing phenomenal growth. We're committing to enterprise class verification logistics. So we're talking multi-site, multi-engine. We're talking high availability database with replication and redundancy. We're talking scalable proxy server interfaces. So depending on the volume of queries, we can always scale up to give very, very high performance. This is a technology that can schedule jobs across all of our engines. It can roll up coverage and other job analytics across all of our engines. And also the platform includes advanced web-based analytics, job controls, and is fully programmable and extensible with a rich library of Python APIs. Another perfect example of verification computational logistics at work is our new Accelerators ML technology. Now, a significant fraction of our customer simulation workloads are at IP level pseudo-randomized benches in UVM or SpecMan. Now, these tests are typically grouped into banks of thousands or even tens of thousands of tests, all firing different pseudo-random stimulus on a common design under test to try to catch corner case bugs. It's very effective and very important part of high quality verification, but it's extremely compute hungry and honestly not very efficient. So it's effective, but it's not efficient. If you really profile that compute, you find that most of it is essentially repetitive. It's generating random stimulus that doesn't actually improve coverage. It's just random stimulus that is covering what has already been covered before with previous random stimulus. So what we've done with Accelerators ML is to build an AI system that can learn from the last time and the time before that you ran your test suites and guide the actual randomization kernel, the underlying solver inside Accelerators, to be smarter the next time you run the regression. So to load the dice, as it were, to nudge it to pick random values that are going to increase coverage faster and more efficiently. Now, it's still early days for us with this technology, but it's looking, extremely encouraging. So let me share for you here some examples with kind of 3 different customer benches, and you can see on the left, a dramatic reduction in total CPU hours to run these suites. And we're talking very large test suites as well. With a massive number, teracycles worth of simulation. But on the other hand, despite this sort of 3 to 5x reduction in total compute, we're pretty much hitting identical coverage numbers. So and our customers have a choice. They can ultimately just, if you like, pocket that compute saving to reduce cost or reduce schedule, or in fact they can take that saving and then redeploy it to do additional verification, more bug hunting, more randomization in other areas. So there's always a trade-off, I think, between kind of performance and coverage, depending on how you want to leverage this technology. And then for those of you with a concern about the quality of that coverage, yes, we do zoom in and look at that closer too. So for example, here is a detailed hit ratio map for one of those tests, showing how, if anything, if you look at it, the hit ratio across all the bins is actually slightly better using AcceleML than it is with the original regression, despite a 5x reduction in the total number of CPU hours. Now, another example of ML at work to improve verification throughput is our Jasper formal. So with formal proof, formal proof algorithms are actually quite similar to how a human would approach proof. There are many different techniques to try to solve an equation or to try to prove a property. And a great mathematician can intuitively see which proof technique or which set of proof techniques are needed to solve a particular equation. So we've done the same thing now with Jasper. We've created a master golden database of proof problems inside Cadence, and we use it to train an AI system to decide kind of intuitively which proof algorithm, and indeed actually which parameters within a proof algorithm, variable, ordering, search depth, backtracing, heuristic, all of those things, what's the best algorithm and the best settings for that algorithm to have the highest chance of solving a particular proof. And again, early days, but it's really very encouraging. We do all this training, it's pre-baked into the product that we ship, but you can see here, it's able to solve 30% more proofs out of the box. We have genuinely made Jasper smarter. We've improved the IQ of our proof solver here. So the last example I'd like to kind of talk with you about is how verification throughput has influenced and inspired our hardware acceleration strategy at Cadence. So we've been a leader in emulation for more than a decade with our flagship Palladium system. Now, Palladium uses a custom proprietary processor we design and tape out here at Cadence. It's the ultimate chip debug accelerator, offering lightning fast, predictable compile and the ability to stop, start, and probe any signal at any time. But now, Palladium has a system level partner, Protium. Protium is targeted at accelerating pre-silicon software debug. So Protium runs much faster than Palladium, but also, like Palladium, is designed for data center deployment. It has a rack-based architecture, and you can scale to multi-billion gate designs with multiple racks connected together. We've designed Protium from the ground up with a unified compile flow to Palladium. So unified transactors, unified hardware bridges, hardware adapter cards for different protocols, USB, PCIe, and so on. to make it as easy as possible to move a design from Palladium to Protium, to get off the truck and onto the plane, as it were, to use our package delivery analogy once again. Now, where Palladium is our customer's ultimate debug machine, Protium is their ultimate performance machine. And they can buy whatever mix of each achieves the highest verification throughput for their specific product needs. So while we're on this topic, I'd actually like to drill down a bit on how each of these two platforms is leveraging a different underlying compute architecture. Since again, I think this is central to that verification throughput mindset. You know, use the right engine for the right job. So the Palladium emulation processor, this custom processor we design, and have done for many generations at Cadence, it's essentially an array of thousands of very simple mini CPUs we call EPs, emulation processing units, all connected together with a switching fabric, a big crossbar switch that allows any EP to compute with any other EP at any time. And then we have dedicated hardware connected to that switching fabric that allows a user to monitor and trace any signal at any time, or to override or force any signal at any time. Compiling to Palladium is a very simple problem of levelizing logic topologically left to right and then stream processing it on these elementary EP units. So the system is highly predictable. If it compiles, if your design compiles, it will run, guaranteed. And it compiles fast and offers amazing simulation-like debug capabilities. Conversely, Protium is leveraging state-of-the-art, high-capacity industry FPGAs comprised of millions of configurable gates. And if you think of, what was the original premise, the original inspiration of an FPGA, it's to deliver the highest possible, most silicon-like performance with a configurable architecture. And so, design once compiled on Protium is much, much faster than on Palladium. But that increased performance comes at the price of a much higher compile effort. You really have to run a full ASIC style place and route for an FPGA, including timing optimization, numerical placement, congestion management, and so on. So you're picking a different point between kind of predictability and debug and performance. And of course, there's no dedicated, at speed debug hardware on the FPGA. So I think you can see the key point of our mindset. Neither architecture, neither engine is better. Just like it's not like a plane is better than a car or a truck. It's just different. And the point is to enable these different engines, make it easy to move from one to the other, and then connect together with some form of logistics management platform that enables you to use the right engine in the right way at the right time. Okay, so I wouldn't want to end this presentation without at least spending a little bit of time and sharing a few words with you all about how computational logistics is in fact one part of an even more encompassing philosophy we have here at Cadence that is truly defining the next chapter of our company. So if you step back from our products themselves, if you think for a moment actually about everything we've spoken about so far here today, and ask the question, what makes the people at Cadence so special? Why are we so unique? How are we able to deliver all this differentiation? And you come to the conclusion that what Cadence has built over that last 30 years since that 1987 IPO filing is one of the world's best computational software teams. We have more than $2.5 billion in revenue and spend almost 40% of this on R&D engineers who know how to write very complex computational software. We have many of the world's experts in numerical solvers, SAT solvers, SMT solvers, graph algorithms, computational geometry, and so on. It is this computational software expertise that is the true wood behind our intelligent system design vision. Honestly speaking, as a computer scientist and lover of algorithms, Cadence's deep expertise and love of computational software is probably why I feel so at home at Cadence. Now, given that this is a design verification conference, I won't digress now into a full overview of how our expertise in computational software is expanding our horizons for the next chapter of Cadence's growth. But I will give just one example, since I think it's still technically a verification example, just not a digital chip verification example. The example is our new Celsius and Clarity system analysis tools, which we launched in 2019. These tools are entirely homegrown at Cadence and build on our deep expertise in advanced, massively parallel matrix solvers in the SPICE and power sign-off markets. With Celsius and Clarity, we leverage this expertise to enter the system analysis market of finite element solvers and fluid dynamics. Celsius and Clarity are disrupting this market with solutions that are just 10x faster and fundamentally more scalable than existing products. So, just to wrap up, thank you all for your time today. It's been a privilege to have the chance to talk with you about Cadence and our intelligent system design strategy. I'll leave you again with that equation. VT equals E times L. Highest verification throughput is the product of best engines with leading logistics. Please take care, stay safe, and stay healthy.